So the exterior angle inequality theorem, again, just kind of know what it says. I don't need you to tell me it's theorem 5-8. If you go to some other school, it's going to be numbered something else. Basically know that that exterior angle has to be bigger than any of the pieces that make it up. Because we already talked about that earlier this year. We know, for example, right here that that is an exterior angle. And we also know which two of those interior angles have to add up to be the same measurement. And those are angles 4 and 3, right? Because those are, what do we call those again? The remote interior, and if you couldn't remember, that's right here. Okay? All right. And so we can kind of answer this one down here then. 1 is equal to 3 plus 4, right? Okay. And so we know for a fact, and if you like numbers, because some people do, let's say this was 100 degrees, and maybe this one here was 50 degrees, and this was, yeah, 50 and 30. That adds to 100, all right. Let's go 60 and 40. Let's say those are the numbers, let's say I gave them to you. I hope you agree with me that angle 1 is definitely bigger than angle 4 all by itself. And it's also bigger than 3 just all by itself. It has to be logically, correct? If you look at the numbers, you can see that that is true here. Okay? And so we know that the measure of angle 1 is greater than the measure of angle 4, or you could say the measure of angle 3. Now, unfortunately, I know a lot of you want to say, don't we also know that it's bigger than angle 2? Well, based on how this is drawn, it looks like it, correct? But watch out for those words, it looks like it. It could be very damaging in mathematics if you try and base all of your information off of that. Oops. Not good enough. What if my picture was that instead? Is 2 still going to be is 1 still bigger than 2? No, not necessarily. Is 1 still bigger than 4? Is 1 still bigger than 3? It is. So I want you to give me the ones that were guaranteed, without a doubt, no matter how the triangle's drawn, it will be true. And we know that angle 4 by itself and angle 3 by itself have to be basically smaller than 1. Or 1 has to be bigger than those. I think it's fairly logical, correct? Well, of course, sometimes the pictures get a little bit more complicated. And the questions get asked in various ways. So here I would like you to list all the angles whose measures must be less than 1. Well, angle 1 is very simple to find. There it is. Are we guaranteed that angle 2 will be less than the measure of angle 1? Are we guaranteed? Could be though, right? But we don't know for sure. We don't want to make any assumptions. Are there any angles up here that we know for sure? Yes, there are a few. Let me draw your attention to that triangle and kind of forget about that stuff for now. It's not down there, okay? Just base your information just off of that for now. 1 is an exterior angle, and I must add 3 and 7 together to get 1, correct? So in other words, 1 must be bigger than 3, and 1 must be bigger than 7. It has to be, right? So it has to be, must be less than 1. Well, angle 3 is one of them, and angle 7 is another one. Do you believe in this picture there are any more that we would know for sure? Yes. 6 and 5, I've been told. Now, how did you come to that conclusion? Well, 1 and 4 might not be the same. They could be. But if you look at it this way, is 1 an exterior angle of now that much bigger green triangle? And I have to add 5 and 6 and 7 together to get to 1 now, right? So if I had to add all 3 of those up to get to 1, 1 must be bigger than any of those individual. Well, we already listed 7, so we don't have to list it again. But we do know that 5 has to be smaller and 6 has to be smaller. Okay, so 5 and 6 is the correct answer. How about 4? Well, which are the ones we haven't talked about? We talked briefly about 2, right? Do we know enough information to decide about 4? Now, if I actually gave you angles, could you go in there and find out? Yeah, but I didn't do that, did I? I didn't say this is 100 degrees, this is 20 degrees. You don't know. And do we know for sure about 8? No, we don't. Is it possible that 1 is actually bigger than some of those? Yes, it's very possible. But we don't know for sure. We want to base it off of what we know for sure. So are there any questions on that? No? Okay. I know it's hard. Sometimes you look at it and you want to say, oh, it looks like it. So now I'm going to switch the question around on you a little bit. List all the angles whose measure must be greater than 2. So I have to find all the angles that have to be bigger than 2. So there's 2. Is 1 guaranteed to be bigger than 2? No, it's not, is it? I know 1 and 2 added together have to be 180, but that's about all I know. So are there angles up here that we know for sure? Yeah, I think there are. And sometimes what you have to do is just focus on one thing at a time. Don't try and get all the answers at once. So if we're talking about angle 8, I must add 2, 7, and 6 together, correct? To get 8? So 8 has to be bigger than 2 all by itself. Okay, so angle 8 is one answer. Is angle 8 the only answer, or is there another one that we would know without a doubt has to be bigger than 2? Yes. Not necessarily. 1 doesn't have to be. Depends on how the triangle's drawn. I could draw it differently so that 1 was not. Yes. Angle 4, I've been told. And how did you come to that conclusion? Yeah. Again, look at a different triangle then. Try and color code it for you. 4 is 2 and 7 added up, correct? So does 4 have to be bigger than 2? Nope, it does. Angle 4. Is that it, or are there more? Again, that we know without a doubt. I was figuring somebody would give me that one. 6 is a very interesting one, but you realize 6 is not an exterior. See, that would count as an exterior angle right there, and that's not where 6 is, right? And all of that would count as an exterior angle, and that's not quite where 6 is, right? It has to be going, one of the sides has to be extended. Doesn't it almost look like 6 is an exterior angle, though? I could see that, okay? But it isn't quite exterior, so we don't know for sure. Okay? Could be, but we don't know. It is actually just 8 and 4. This is the best we could do. I want you to think about this next one for a second or two. Most people can give me the right answer. What most people can't do? I think I made the answer fairly obvious, but can you support your answer? That's the question. So take it a second or two right now and see if you can come up with a way to support your answer to that question. Which is bigger? I am assuming that was enough time. So I think we can all give the answer. Which is greater, 7 or 8? And obviously it's 8. But how do you justify that? How do you convince somebody that that's the case? Yes. Okay, and therefore 8 must be bigger than 7 by itself. Very good. Okay, and that is one way to do it. What was basically said was that we know 2 plus 7 equals 4, and 4 plus 6 equals 8, so then 8 must be bigger than 7 all by itself. Is that logical? Yes, very much so. Another way that you could have gone about that, I like that way though. Another way you could have looked at it is that to get 8, I have to add 2, 7, and 6, right? Basically the same argument, right? Because she's just saying 2 and 7 is 4, and it works out the same way. And basically, yeah, you could just say that measure of angle 2 plus the measure of angle 7 plus the measure of angle 6 equals the measure of angle 8. Therefore, that's always a good word to put in your proofs. Whether or not they're right or not, it just sounds convincing. You know. Therefore, the measure of angle 8, and that's not an angle symbol, is it? Measure of angle 8 is greater than the measure of angle 7 by itself. Okay. It probably, if you had to do this in a proof, it would take quite a few more steps than that, but that's in general pretty good convincing. Okay. Any questions so far? All right. So that's kind of it for the exterior angle deal, but it still deals with some logic, you know, what's bigger than what. This is working backwards, so they're basically saying we started with some number. We can maybe say that number was right here. We don't know what it was, but we started with that number, we increased it by 21, multiplied it by 3, then subtracted 9, then divided by 5. When I was all done, I got 30. But the question is what number did I start with? Obviously, you could guess and check, right? But you might be here for a while. Just start, oh, maybe it was 2, and try it and see if it works, right? Or what you could do is simply undo everything you just did, right? So let's start basically at the end. I know that's a very weird saying, but start where you finished and go backwards, which is why they call this working backwards. So what's the very last thing I did to actually get to 30? Was divide by 5, right? So let's undo that. And how do you undo dividing by 5? You multiply by 5. Okay? And that is 150. Undone. Because you can't just undo these in any order, right? You have to do it in the exact order, the opposite order of which they were done. Before that, I subtracted 9. So to undo that, we will add 9, of course. And then I'll just move it up here so everybody can see it. That's been undone. Multiply by 3. So to undo that, we must divide by 3. Okay? And for those that have forgotten this skill, 3 goes into 1, doesn't. 3 goes into 15 5 times. Put the 15 down here, subtract. Bring down the 9. 3 goes in 3 times. It actually is exactly 9, so remainder 0. Right? So the answer is 53. Right? So that's been undone. Increase the number by 21. Well, how do you undo increasing? Well, you do the opposite, which is decrease, but we know that as subtraction. And 3 minus 1, that's 2. 5 minus 2 is 3. Apparently, we started at the number 32. The best part about these problems is they're so easy to check. Just start at 32, do all that stuff, and see if you end up at 30. Okay, that's what should happen. Okay. So again, you just kind of undo them in the opposite order of what they were done. Okay. So why don't you try the next one right now? Take a little bit of time. Do it on your own. See if you can do it. I saw a lot of you with the correct answer, so that's good. So where did we end up? We ended up at 100. All right, so we have to undo that. So divide by 5, which is 20. There we go. Undone. So they added 17, so we subtract. That's 3. Undone. Divide by 2, so we're going to multiply by 2. 6. Undone. Again, we'll move it up so everybody can see it. Decrease by 5, so we're going to increase by 5. And 11 is where you started. Okay. Any questions on that? The next, what we're actually going to do is, I think it's second on your sheet. We're going to do this one first, is to add, basically find the sum of the first 100 positive integers. Might want to add that in there. Because remember, integers go positive and negative, so that adding up the first 100 would be kind of difficult if they go positive and negative infinity. That's kind of tough. That particular problem right there, and there's a story behind it. I know some of you may have done it in Algebra 2. That particular problem was given to a young man quite a long time ago. And it was given to him because he was incredibly smart and was kind of annoying the teacher. And the teacher said, here, figure this out. Add up the first 100 integers. And the teacher expected this young man to go 1 plus 2 plus 3. Obviously, he did not have calculators back then. Okay? And the teacher figured it would take him most of the day to do this. And imagine to the surprise when it was, the story goes that it was approximately 20 or 30 seconds later when he raised his hand with the answer. Okay. I've been talking way more than that about this problem. So incredibly impressive. So obviously he didn't go 1 plus 2 plus 3 plus 4 plus 5. Okay. His name was Gauss, his last name, and he came up with a lot of number theory. And he did this when he was about your age or a little younger, is when he did this. Again, without the use of any calculating device at all. Okay. He very quickly noticed a pattern. He was very good at this, taking somewhat complicated problems and making them very simple. Here's what he did. He said, well, what's the first integer? First positive integer is 1. And what's the last one they want me to add up? 100. He said, you know what? That adds up to 101. What if I take the second integer, 2, and I add it to the not last, but second to last? I get the same thing. What if I keep doing that? eventually wouldn't I write down all the numbers from 1 to 100? And he said, well, I'm not going to do that. That's ridiculous, he said. I'm just going to kind of say, well, how far do I have to go until I've actually written down every number from 1 to 100? Do I go all the way to 100 here and then a 1 over there? If you do that, you've written them down all twice, right? So you don't go that far. How far do you go? You only go part way, right? And how far is it in this case? You go until you write down 50 plus 51, correct? Oh, amazingly, that also equals 101. So do you agree that 1 through 50 are here and 51 through 100 are over there? Correct? They have all been written down. Well, in theory, all been written down. And they all, if I pair them like that, add to 101. And if I actually wrote them all out, how many little pairs like that would I have? I'd have 50 of those little pairs, right? So he said, let's take 101 times 50, which is quite simple to do in your head. And he did that with 0 instruction on his own in approximately 30 seconds. And the best part of the story is when the teacher came over, obviously disgusted, probably thinking that he had a question or something. And then he had an answer. The teacher didn't even know if it was right or not. And then he showed what he did, and the teacher was like, yep, that's probably right. And I don't know, maybe sent him home or something, I don't really know. So that little theory can be applied to any kind of problem when you want to kind of add things up. So do you think that you can apply that particular theory to the first problem on yours, which is the first 200? Can you apply the same idea? Well, let's see if you can. Give it a shot. Again, first one, last one, what does it add to? How far do you got to go? Things like that are the things you have to think of. So once again, we will have a guest presenter for the second example here. Let's see how she does. First positive 200 integers. As I said while you were working, it's not just double the other answer. And we'll talk about that when our presenter gets done. And I'm starting not to like it. Every guest presenter has better handwriting than me. I don't know. That's not saying much for me. Okay, so she said 100 plus 200 is 201, which is very true. She's saying, well, she knew that 100 and 101 would be the last one she would have to do. And so she's multiplying it out. Once again, the multiplying not too difficult, right? Could be done in your head. So 20,100, is that correct? Yes, it is. That's very much correct. Do you notice that's nowhere near double 50-50, is it? Why isn't it just double? That's what some people think. Oh, you're going to 200. Why isn't it just twice as big? Well, when you're adding 1 to 100, you're just adding 1 to 100. What am I actually adding or tacking on top of that number? 101 to 200, correct? If I add that up, that's considerably larger. Now, you could actually use this little formula to do that as well, but what if all I wanted was 101 to 200? How could I find that answer? Quite simply with the numbers I have on the board. Somebody said it. If I wanted 101 to 200, how would I figure that out? Just the sum, yeah. Yeah, take 20,100, which is all 200, and subtract the first 100, which is 50-50. That would tell you how much is just from 101 to 200. Now, Gauss very quickly after that came up with a formula that's used in sequence and series problems, and he basically said the sum of any number of terms, and you don't have to write this down, but you can if you want, is equal to, take however many terms you have and divide it by 2. Did I do that anywhere in this problem? Take the number of terms I have and divide it by 2. Where did that happen in each of these problems? 50, and where did it happen over here? 100, right? Isn't that half of how many terms I was going to have? And he said, let's take that times whatever the first term, this is an A, by the way, A sub 1, added to the last term is. Is that what we did? Took the first term, added it to the last term, and then multiplied by basically half the number of terms we had. That's exactly what we did. Okay. So if you know the first and the last, whichever terms you want, and you know how many terms there are, you can add up any ones you want. Okay? That's quite amazing. So that's another way you could have gotten from 101 to 200. First term's 101, last term's 200. Would have worked. So any questions on making a problem smaller? He was amazing at doing that. Working backwards, or exterior angles. I guess it's kind of a mixture of lots of things, right? All right.